very simple, very easy. If you understand exactly what we have inside the CPU. Because when we identify this one in the first class, we said it's the interface between the computer hardware and the computer software. It's the interface between the software and the hardware. Today, we'll see what this means exactly. In the other way, when you write, for example, in Java or any system.out or print, for example, in Python, print, I want to print X. Now this one will be converted to 01 binary. The CPU will understand that this one means a print. So what is this? The instruction set architecture, the ISA actually. Finally, we will look to the addressing type, how we can access a specific address in the memory, and for sure the access methods will be 10 marks final exam question, 100% this one, and it's very simple. You will solve this question within 2 or 3 minutes maximum, you will see. So, we will start with the CPU. Basics, organization, main component, what's the bus, what's the clock, the input-output subsystem, memory organization and addressing. We have a simple calculation here. Interrupts, they will not be discussed at all. Mary, it's the simple programming language. Use the assembler. What's the instruction processing? We will have a look to a simple and basic program written in Mary. After that, we'll extend our program. In the other way, we'll study in the beginning 9 instructions in Mary. After that, we'll add another 4 instructions. So the total actually is 13, not 14 also. Addressing modes will be the next class. It's not needed for the TMA, so we can postpone this one. But it's very important for the final exam, the addressing mode. And the Mary, for sure they will either ask you to write a program or they will ask you what's the output. So in chapter 1, 2, 3, we learn about the computer system, the computer component, how the data is stored, how the data is processed, how we can represent the numbers, the numbering system, the conversion between them, the gates, the combinational circuits, the sequential circuits, okay, decoder, B flip-flop, set reset, JK flip-flop, and so on. Now, we will see or we will focus on the following, how the computer components works, especially the CPU, and how they fit together, how they work together to provide me with a computer system. Now, a quick revision. What's the main component of the computer system? What's the architecture of the computer system? The exam tomorrow, ya Jama'ah. What's the main component of the computer system? الامتحان بكرة. بكرة الامتحان. شغلتين. 2 things. How they fit together. Processor. في شغلة ثانية يا معتز. Main memory. Thank you. Done. Do not write anything else. Exactly. So we'll see how the memory and the processor work together in this class. So based on the von Neumann architecture, which discussed before, it satisfies at least the following characteristics. Now, the main computer hardware contains a central processing unit and main memory, and for sure input and output devices now. Now, the central processing unit itself divided into 3 subcomponents. Control unit, ALU, arithmetic logic unit, وحدة حساب ومنطق, and the most important one, registers. And you need to know from now the registers located inside the CPU. They are a memory storage device, okay, located inside the CPU. They are very fast and very expensive. Where? Inside the CPU. Now main memory will hold the program that control the computer's operation. Now, for this file, all the data related to this file loaded from the hard disk to the computer main memory. The data related to this slide number 6, it's loaded from the main memory inside the CPU itself. Now, for sure, based on von Neumann architecture, we have a CPU, we have a main memory, we have input-output device. Now, capacity to carry out sequential instruction processing, what does that mean? The default execution for any set of instructions is a sequential. Number 1, 2, 3, 4, 5, and so on. Can we control it? Yes, we can control it by using the if clause, the selection, or we can use the while, the for, the repetition. It's not our business in this course. Now, between these components, we have a connection. So it can be a single path connection, for example, between the main memory and the CPU, the control unit. And we will see what does a single path connection between the main memory and the CPU means. Now here in slide 7, it's just repeated as it is, so we'll not add any comments. Now, this is how the architecture looks like. We have an input-output devices, and you need to know that there is a direct connect. In some cases, there is a direct communication between input-output devices and the ALU inside the CPU. Why? Because we have a special registers can take the input from the keyboard directly to the CPU. Some registers can directly send the data from the CPU to the output device. Because of this, we have a direct connection here. Hello? مين مش سامعني؟ غير فاطمة، مين مش سامعني يا جماعة؟ Can you hear me? Can you hear me? طيب سامعيني. طيب كيف بدنا نقول لفاطمة؟ فاطمة check your sorry. So, just let me back to the previous one. Now, we have a CPU. As you see, we have a direct connection between the ALU and the registers. Control unit manage everything inside the CPU, and it has a common path. Direct connection between the main memory and the CPU through the control unit. As you see, it's the two-way connection. What does that mean? I can send from the CPU to the computer main memory, or I can retrieve data or instruction from the computer main memory to the CPU. Now, if I want to execute something, what the CPU will do? For example, I want to do add 4 plus 5. Now, what the CPU will do, this is the CPU. To understand this, the coming 15 slides will be very simple, if you understand this. Now, in the main memory, we have this here. Add 4 plus 5. Okay, now, the CPU will fetch this instruction, which means we will load it here inside a special register called IR, instruction register. After we load this instruction inside the CPU, there is another register called the program counter. Always the value of this one, the next instruction to be executed. So if this instruction is number 5, the program counter value will be 6. So the first step, the CPU will fetch, copy the instruction inside the CPU. Now the CPU do not understand add. There is nothing called add for the CPU. The CPU understands 0 and 1. So the CPU in the next step will decode the instruction, convert it to a language that CPU can understand. Is it clear until now? So fetch, decode. Decode, convert it to a language the CPU can understand. Finally, the CPU will check, do I need any another data? Yes, when we translate it, it will be an instruction set architecture, the ISA. Exactly. After we decode it, Yamotas. Exactly. Now the CPU will check, do I need any extra data for the command add? Yes. I need number 5 and I need number 4. So once I have everything inside the CPU, fetch, decode, retrieve the extra data, I can execute it. I can execute this. So we will have number 9 inside register called AC, accumulator. So if we want to save the result, we will send this result to another new location in the memory. So the CPU mainly go through three main steps: fetch, decode, execute. What we call this a CPU cycle. So in each cycle, when we say the CPU can perform 2.4 billion cycle in second, the CPU can execute 2.4 billion fetch, decode, execute in 1 second. Is it clear? It's very important. If you understand this, the next will be very simple. So this is how the CPU execute any instruction: fetch, decode, execute. So the program instruction is stored inside the main memory. Any instruction will be in the main memory. Now the machine will run the program sequentially, which means the default execution for any program is a sequential execution. Now, based on the von Neumann execution cycle, what's the von Neumann or what's the CPU cycle? It's called fetch, decode, execute cycle. Now, in each iteration, in each cycle, in one cycle, what will happen exactly? If this is the cycle number 1. First step, the control unit fetch يعني بتأخذ, retrieve the next instruction or the next program instruction from the memory using the program counter to determine where the instruction is located. Remember, I told you the value of the program counter is the next instruction to be executed. Suppose it's 6. So the control unit will go to the computer main memory, will fetch the instruction number 6 inside the IR. It's not directly from the CPU to the IR. Later you will see how. Once we fetch the instruction, the program counter will be 7, the next instruction to be executed. So this is the first step. Second step, the instruction will be decoded. Decoded means it will be translated into a language the ARU can understand. In the other way, the instruction will be converted to ISA. It will become a 0, 1. Now, we will look if any other data is needed, we will fetch that data from the memory inside some registers inside the CPU. Once we have the instruction, once we already decoded, once we fetch the other data, the ARU will execute the instruction. And the result will be placed inside the special register here called AC, accumulator. Later it will be sent to the main memory. Any question? Any question here? Clear? طيب ممتاز. Now, so during the fetch, the control unit will look to the value of the program counter. If the value of the program counter, okay, PC program counter, this one is a special register. It's a register inside the CPU. Indicate which instruction to be fetched now. Now the value is 3. So we will load the 3, the instruction number 3 inside what? The CPU. What's the program counter value will become? Once we fetch it, what's the value? 4. Directly will be increased by 1. Sequential execution. Sequential. So it will become 4, the program counter. Once we fetch the instruction, we need to decode it. Decode it, convert the instruction to a value, the CPU, or to format the CPU, understand the ALU. Then we will look, do we need any extra data for this instruction? If yes, we will load it. Everything is done. Everything will be controlled by the control unit, by the way. We can go to the last step, execute the instruction, and place the result into a register, or it can be directly to the memory. But mainly, usually, we will what? Place the result inside the register called accumulator, then to the output. And sometimes, if we use a special register called output register, it will be placed directly from the CPU to the output device. So the central processing unit responsible for fetching the program instruction, decoding each instruction that is fetched, and finally performing the indicated sequence of the correct data. So the computer CPU fetch the program instruction, decode the instruction that fetch, finally execute the indicated sequence of the operation on data. Is it clear until now? Any question? What we call this? A CPU cycle, von Neumann cycle, a CPU iteration. Clear? Now, we have two important principles of the CPU, data path and control unit. It's very important. The CPU will fetch, will send the result. So we need a connection to send and receive a data. So it's the data path. All the computer components should be controlled. So the control unit task. So two main principles now, data path and control unit. Data path contains or consisting the ALU and the network of the storage unit, the registers that are interconnected by data bus that is also connected to the main memory. So data bus, ALU, registers connected by data bus to the main memory through the control unit. Now, second one, the control unit, responsible for sequencing the operation, check the program counter value, based on the value we'll fetch the memory, then we will increment the program counter by 1. This is the default execution type. And make sure that the correct data is in the correct location when we need it at that correct time. Now, what are the registers? Is a special whole data memory, can be accessed very fast by the CPU. Why? Because they are located inside the CPU actually. And they are places to store a wide variety of data, different type of data. Can be numeric data, can be address, can be control information, and so on. And you need to know that the control unit can access directly any data inside the register. Any data can be accessed quickly by the control unit. Now, in general, the registers divided into two main types: special purpose register and general register. Now, what does general registers mean? These registers available to the programmer. In the other way, we can put any data type inside this register. Any data type. Special purpose register always store the same data type. I will give you an example. For a special purpose register, the program counter actually, it's a register. What we have inside it, always the value of the program counter, the next instruction to be executed, the next instruction. So always what's the data type will be? Number. Always. So it's a special purpose register. Special purpose register. For example, the index register, the status registers are special purpose register in the status on off. So same data type always. Now how we implement the registers? We implement them at the hardware level by using the D flip-flop. And remember, for the D flip-flop, it's 1 bit at each time. So if we have a register with 32 bits, we need 32 D flip-flop to implement that register. Now the most important comment is, if your system is 32 bits, the word size, you know what's the word size in the computer? Or 64 bits. You know what's the word size? Do you know what's this? T170, 150. Word size is the maximum amount of data the CPU can process in one cycle. So if your system 32 bits, so the total number of the register's capacity 32 bits. If your system 64, what's the maximum capacity? It's 64. So actually 32, 64 word size referring to what? To the storage capacity of the registers inside the CPU. Because we say the word size is the maximum number of data the CPU can process in a unit of time. This is how we identify it. Now ALU, from its name, وحدة حساب ومنطق, so all the arithmetic and the logical operations are directly executed by the ALU, and it's controlled by the control unit. The registers controlled by the control unit. The communication between the ALU, the registers, and the main memory controlled by the control unit. Everything controlled by the control unit. The manager of the computer system at all, the control unit. So the control unit determines which action to carry or to execute according to the value inside the program counter. For the last time, program counter, not the current instruction, always the value of the program counter, the next instruction to be executed, the next one. So if we fetch number 6, the value of the program counter 7. If we fetch the instruction 10, the value of the PC 11, not 10. So control unit, it fetches and decodes sequentially the instruction in the main memory. We can control the sequential execution. We can control it by using the special instruction in memory like jump X or jump and store. 2 instructions that. It will also, the control unit monitors the execution of these instructions and the transfer of the information. In the other way, everything under the control of the control unit. Now we know that the hardware component communicating with each other by using a bus line or bus lines, by using buses. If there is no buses, means there is no communication between the hardware. We cannot exchange the data at all. So the CPU communicates with each other, or sorry, the CPU components communicate with each other by using a bus. Moreover, in order to maintain the synchronization of the activity, the CPU contains at least one clock. Do you know what's the clock here? The clock tick. At each clock tick, like the JK flip-flop, the feedback, the CPU will go what? On a cycle, fetch, decode, execute. So in 1 second, we have 2.4 billion clock tick, 2.4 billion cycle. Buses is a set of wires that at the same time simultaneously carry, transmit, convey, deliver a single bit along each line. So the buses actually simply, it's a multiple lines between the hardware. And what's the maximum capacity of each line? Single bit. So 0, 1, 0, 1, 1, 0. All of these will be sent at the same time from the source to the destination. So it connects a multiple subsystem within the system. Now, a bus or the bus can be point to point or it can be multi-point, which means one-to-one connection or shared connection. In case it's shared, actually, we call it the common pathway. Or the shared connection. Now we will understand this exactly. Now check this one, point-to-point bus. It's like the serial board. For example, a serial, or if we use the serial between the computer and the printer, point-to-point connection. For example, the modem connection. So it's a serial, one-to-one, point-to-point, between the ALU and the control unit. It's one-to-one. I do not want to move back, but I will. So we have, if you remember, when we explain it, we have a connection, one-to-one connection between the ALU and the control unit. So this is a common, or one-to-one, point-to-point, connection. The common pathway, it's a shared connection. Shared. Or before we go to the common pathway, the multi-point bus or the common pathway is same. It's shared between multiple devices. For example, this is the common pathway or the multi-point. CPU, computer main memory, hard disk, any controller or any other disk will share the same connection. So be careful when we use this type of connection. We need some protocol to manage the access of this multi-point bus between the devices. The other way, we need something called access control protocol. Like the wireless. Now, we cannot all of us access the wireless connection. There is an access control protocol to authenticate the user and let the user connect to the access point. So we have an access control to the multi-point bus. Now, mainly, what are the components of the bus? What are the main components of any bus, regardless of its point-to-point or multi-point? It will contain a data lines. From its name, data lines. So these lines are dedicated to move the data, the actual information that moves. So here, for example, between the CPU and the main memory, we have the data bus, this one. So the data will be exchanged through this bus or line. We have control lines, indicate which device has the permission to use the bus and for what. So we say, when I want to give you an access to the multi-point bus, we need to control who can access that one by using the control line. Address line, in which location the data should be retrieved or read from. Now, This is the main memory, right? Remember, address, data. So, which address should I read the data from, or which address should I write a data on? Either we read or write. Finally, power lines, because it's electricity, we need an electrical power to perform the main task. Clock. Every computer contains at least one clock that synchronizes the activity of its component. The CPU requires a fixed number of clock ticks, and at each clock tick, we will go through fetch, decode, execute. Now this one is very important. The CPU requires a fixed number of clock ticks to execute each instruction. No, it's incorrect. Remove each. Why? Why remove each? Because, for example, some instructions, for example, instruction 10, it will need 1 million clock ticks. Some of them, some instruction will need, for example, 2 multiplied by 10 to the power 9 cycles, 2 seconds. So, if we can execute each instruction in each cycle, so actually no need to the clock. In each cycle, the CPU will complete instruction. So, that means the regular PC will be not a supercomputer, super cluster, not supercomputer. It's not logical. So remember, in each cycle or in each clock, we will do fetch, decode, execute. Some instructions can be done within a single cycle. Some of them millions, some of them thousands, some of them whatever. We are not sure. We cannot guarantee that each instruction will need one cycle. It's incorrect at all. Now, what's the clock frequency? How many cycles we have in 1 second? How many cycles in 1 second? This is the frequency. Now, I'm not sure if you are studying a communication courses. Have you studied T105A course or T105B? T105B or A. Now, in the network, this is how we represent the cycle actually, by using the sine wave, okay? If we start from this point, go high, low, reach the same point, this is a cycle. For example, if I start from here, I will go low, high, I'm reaching the same point now here. From here to here, it's a cycle. Now, how many cycles I can repeat in 1 second? It's the frequency. We call it the frequency. So the clock frequency mainly measures in hertz, kilohertz, megahertz, but now we reach the gigahertz. So when we say the clock or the CPU speed 2.4 gigahertz, 2.4 multiplied by 10 to the power 9 cycle in 1 second. What is this? The frequency. Now, each cycle needs a time. We call it a period. Now, there is reciprocal relation between the frequency and the time. What does that mean? علاقة عكسية. F equal 1 over T. T, the time needed for the cycle, equal 1 over F. I do not want you to think about it in full detail. Just you need to know frequency clock, how many clock tick in 1 second. Each clock, each cycle need a time. What we call this time? The clock cycle time. So what's the relation between the cycle time and the number of cycles? Reciprocal, عكسي. So if the clock cycle need a very short time, so we have more cycles. If each cycle need a long time, we have a less cycles, less frequency. So T equal 1 over F, F equal 1 over T. For example, here they said we have 800 mega clock. An 800 megahertz clock has a cycle time of what? If the CPU equal 800 megahertz. So what's the time for the cycle? 1 over 800. This is the frequency. Now I want to convert it from mega to kilohertz to hertz. So 1 over 800 multiplied by 10 to the power 6. So it will be 1.25 nanosecond. Milli, micro, nano, 10 to the power 9. If, for example, the cycle time is 2 nanoseconds, so how many mega, or what's the frequency? 1 over 2 multiplied by 10 to the power 6, because they said it's mega. So it's 500 mega. Calculate it, it will give you 500. Okay, so F equal 1 over T, T equal 1 over F. Any question? Any question? طلاب معي انتو؟ معي أكيد البقية معي. Before I start with this part, are you here? ولا just login يعني؟ طيب. Whatever I'm going to discuss is very important now. It's very, very important for the final exam. The memory addressing. Now, what I told you about the memory. Memory is set of rows, multiple holding area. For each row, what we have, do not forget this, address and data. Okay? Now we are going to talk about this. Now, memory addressing. Memory can be a byte addressable or word addressable, where the word typically contains or consists of 2 or more bytes. Now, this address, when it's byte addressable, which means the size is 1 byte. I'm talking about this, the address only, okay? If the memory addressing mode, byte addressable, which means the size of each address, 1 byte, 8 bits. So 8 bits here, 8 bits for each line, the address 8 bits. Now, if it's word addressable, which means the size either 16 bits, 2 bytes, or 32 bits, or 64 bits. So 2 bytes, 4 bytes, 8 bytes. Is it clear, Hai? Is it clear? So byte addressable, each byte has its own address. Each address contains 8 bits, or each memory row, contain 8 bits. Word addressable, each word, each line is unique. Each line is unique. Okay? Each memory row contains 1 word that can be larger than 8 bits. In the other way, each row will be more than 8 bits. Now, how many address and how many address bit do we have in the given memory? Now, before we go to this, when I said it's a byte addressable, when I say it's a byte addressable, the address will not be 8 bits. The full row will be 8 bits. Some of them will be for the data, and some of the bits will be for the address. When the address is word addressable, for example 32, so the row is 32 bits. Some of the bits will be for the address and some of the bits will be for the data. Okay? Is it clear? Now the question is the following. How many addresses we have in a given memory and how many bits for each address? To calculate or understand this question, to answer this question, you need some input. What's the input? To answer this question, in the question, they must give you or tell you what's the type of the address. So in the question, they will say it's a word addressable or byte addressable. Also, they must give you what's the word size. The word size, 1 bit, byte addressable, 8 bits or 16 bits, 32 bits, 64 bits. Now, the storage capacity, the capacity of the computer main memory. This is the computer main memory, okay? The capacity will be represented by the notation L multiplied by W. Long multiplied by the width. The length multiplied by the length. So if it's 4M, for example, 4M, it means 4M by 16. Sorry, it's 4M multiplied by 16. So the length is 4 mega. The width of each row, 16 bits. So these 16 bits will be divided in each row into 2 parts, address and data. Clear? Until now, clear? Right. Now this is the question. How is 4 mega multiplied by 16 word addressable memory organized? How many bits per address we have if we have 4 mega by 16? The answer is very simple now. They said word addressable. So directly the word size will be what? The word size will be 16. Okay? Now 4 mega multiplied by 16. Now, how we will represent it? This one is the word size. Take it out. Why you will take it out? Because it's a word addressable. If it's byte addressable, we will keep it. Now, take the 4M. I have very simple question. Is the 4 2 to the power 2? Yes or no? Yes. M, is it 2 to the power 20? One mega, 2 to the power 20? Yes, 2 to the power 20. This one is 2, not 1. 2. So, 4M actually, it's 2 to the power 22. Correct? Is it correct? So is it clear how I got 2 to the power 22? Right. What we will say now? What we will say? Each address for each memory location is 22 bits. Done. We solved that question. Now one more time, because it's a word addressable. Now back to the memory. Data, it will equal the word size. The address, we need to calculate it. We need to calculate the address. It's not 32 bits all. If it's a word addressable, byte addressable, the data will be 8 bits. If it's a byte addressable, the data will be equal the byte size. Now, how many bits here? We need to calculate it. When they said 8m times 16, now 16 is the data. Why? Because it's word addressable. If it's a byte addressable, we will not calculate it like this. Now 4 is 2 to the power 2. Mega, from mega to kilo to byte, we have 2 to the power 20. So multiplied by 2 to the power 20 equal 2 to the power 22. So each address needs the 22 bits. So the first address will be 22, 0. The last address will be 2 to the power 22 minus 1 because we start from zeros. Clear? So each address will be represented by 22 bits. Clear? أكيد. One more question. How many bits you need to address 2m by 32? How many bits we need if we have 2m multiplied by 32? If it is byte addressable, if it is word addressable. Okay? Now, 32 bits, how many bytes? Now the first pass, it's a byte addressable. So 2m multiplied by what? It's a byte addressable. So 32 divided by 8 equal 4. So it's 2m by 4. So 2, it's 2 to the power 1. M, 2 to the power 20. 4, it's 2 to the power 2. So we take this one because it's a byte addressable. So 2 to the power 23. So we need the 23 bits for each address when we have this memory, and the address type is byte addressable. Byte addressable. Now 2m multiplied by 32, and it's a word addressable. Once they say it's a word addressable, delete this. So it's only 2m. 2 to the power 1 multiplied by 2 to the power 20 equal 2 to the power 21. So we need 21 bits per address. Clear? واضح ولا لا؟ أكيد واضح. يعني التريك بسيطة جدا. إذا ميموري بايت هذا راح نحوله لبايت ويدخل بعملية التحويل. إذا قال لي وورد ادريسابل انسى الويب، بس خد اللينك. كلير؟ آخر مرة يا جماعة. أي حد عنده سؤال؟ خلاص. أوكي. طيب memory organization, usually the computer's physical memory will not be made by using a single chip capacity or high capacity chip. Usually we divide the memory into group of capacities, or we divide it into small capacities chip to make the access faster and to provide a better performance. Access is more efficient when the memory is organized in a bank of chips with the addresses interleaved across the chip. Yeah, what they mean? This is how the RAM looks like. Now you see we have a black chips here. Okay? they said instead of, okay, have a RAM with a single chip, we will divide it into multiple chips. Why? The access time here better than the access time here. So, to understand it clearly, how we can build 32 kilo by 16 word addressable. But by the way, if this one should be converted, now can you tell me how we can, if we have 32k by 16, how many address we have? If it's what they say, it's a word addressable. Word addressable. One more example, 32k by 16 word addressable. Word addressable, we do not need this one. 2 to the power 5 multiplied by 2 to the power 10 equals 2 to the power 15. So we need 15 bits per address. So, how we will build this 32k times 16 with only 2k times 8 RAM chip. If each RAM chip give me 2k times 8, and they want to achieve to have a total capacity 32 times 16. So what I will do, it's very simple. I will have two rows, two columns, sorry. In each column I have 2k by 8 and this one 2k by 8. So 8 plus 8 in each row 16. So done. We solve the 16. Now to achieve 32, how many rows I need here? 16. From 0 to 15. Because of this we say this 15 bits. And here we have another 16 rows. So 16 plus 16, 32. So 32k times 16 word addressable RAM memory can be created with 32 different 2k times 8. So you could connect 16 rows and 2 columns in order to get the total capacity. So 16 rows, 2 columns will give me what? 32k times 16. Now, just a minute, 1 minute please. Okay, now we'll start with the Mary, the assembler. We'll see if we can explain an example today or not based on our progress. So we'll have an introduction, what's the instruction set architecture. Before that we need to understand how many registers and what's the type of each register inside the CPU, and understand how each register is working in a specific instruction based on the Mary cases. Now, we are familiar with the computer component, but how these components connected together, how they work together, now we will explain. Leonardo da Vinci said, when you wish to produce a result by means of an instrument, for example, you want to design a machine to get some result, do not allow yourself to complicate it. In the other way, you want to build a machine to get a specific result. Make it simple as much as you can. Okay? Once you get the required result, done. What does that mean? It's not always, if you make the things, it's not correct, not always. Do not think that as long or as far as you make what you design very complicated, you will get a better performance. No. As much as you make it simple, straightforward, clear, you will get the result correctly, more accurate. So this is the Mary. Mary is a machine instruction that is really intuitive, simple, بدائية, and easy. So a very simple architecture, Mary, and its ISA, instruction set architecture, are represented to allow you to get a full understanding about the basic architectural organization involved in the program. Now we need to know that Mary exhibits the classical von Neumann design, which means I have fetch, decode, execute, I have control unit, main memory, input, out, programs. So we have something called the program counter, accumulator, instruction set register, memory address register, memory buffer register, input register, output register. Don't worry, I'm going to explain each one of these. So the total number is 4096 bytes of memory and 2 addressing modes, word addressable, byte addressable. Assembly language programming is introduced to reinforce the concepts of instruction format, instruction mode, data format, and control that are presented here. Now, no problem here, it's only an introduction. Let us start with the most important part. What you see here is the registers we are going to use when we write a Mary code. If you really understand what's the task of each register, you can write any code, you can trace any code, you can answer any question very fast and simple. Now, the first register is called BC, the program counter. Always the value of this register, the next instruction to be executed. The next one, not the current one we executed in the CPU. Which one will be next executed now? IR instruction register. So when we fetch instruction, the final location after we decode it, not when we fetch it, after we decode the instruction, convert it to 01 language, it will be loaded inside the instruction register. Now, memory address register, its reference to specific address in the main memory. Memory address register, the address of the data we need to retrieve from or we need to write on. Now we save the memory divided to address and data. This address will be loaded inside the CPU on the memory address register. So what about the data? Before we convert it to either it will be loaded or we can write to the main memory by using the memory buffer register. So memory address register, the address of the data we need to read or the location of the memory where we need to store data. Memory buffer register, either we are copying the data to the memory buffer register or we are what? Sending from the CPU to the computer memory. Output register, directly from the CPU to the output device. Print the result. Input register, from the keyboard to the CPU. Now the most important one is this one, the accumulator. Now what's the accumulator? Suppose we have this add 5 plus 4. One of these will be loaded inside the accumulator. Suppose we calculate 5 plus 4. We know it's 9. The result will be inside the accumulator. So the accumulator is single value operand. Either it can be one of the operands for the instruction, or it can be the final result. So how I can read the specific data from the CPU if I have these registers? First step, we'll check what's the program counter value. It's 6. So we'll go to the computer main memory where the instruction set is located. We'll copy its address to the memory address register. Now the program counter value will be 7. Now we will copy the data at that address which loaded inside the MAR to the MBR from the main memory to the memory buffer register. Now the accumulator wants to use this data, we will send it to the accumulator. We execute the operation, we get the result from the accumulator to the memory buffer register, from the memory buffer register to the computer main memory, but in this address. IR, to execute this instruction, we need to decode it inside the instruction register. So, we have how many registers? 7 registers. So, the memory architecture has the following characteristics before we start. Binary, 2's complement data representation. They use the 2 complement. Stored program, fixed word linked data and instruction. 4K times 16 word addressable main memory, 16 bits instruction. Now do not forget this one. Each instruction inside the instruction register, it will contain 16 bits only. These 16 bits will be divided into 2 parts. We will talk about it later. So what's the size of the IR? 16 bits. 16 bits arithmetic logic unit, the accumulator is 16 bits as well. So 7 registers to control the movement of that. Now, I think the slide is here. Okay, it's here. Good. Now, registers, as you know, it's a storage area located inside the CPU. The ALU portion of the CPU perform all the processing. In the other way, the ALU, it's a part of the CPU, it's not the CPU. We have a 7 registers who will use it when we execute the programs. The first register, one more time, is the accumulator. The size is 16 bits register that hold the conditional operator less than, greater than, equal, or one operand of 2 instructions. As I said, one operand, if we have 5 plus 6, one of these will be what? Inside the accumulator, one of these. If we want to check x greater than or equal 5, so the value, this one that we are checking, will be inside the accumulator. Because of this, they said what? They hold the condition operator. Memory address register. It's a 12-bit register that holds the memory address of the instruction or the operand of the instruction. So either it's an address to instruction we want to execute it, or it's address of what? Of data. We need to access that data. Memory buffer register, 16-bit register, hold the data after it's retrieved from the main memory or before we send it to the main memory. So if we read the data, we will read it from the main memory to the memory buffer register. If we want to store data, we will send it to the memory buffer register, from the memory buffer register to the computer main memory. If you understand this, the Mary code will be very simple. Now, program counter, it's a 12-bit register that holds the address of next instruction to be executed, not the current one. Instruction register is 16-bit that holds the instruction we are executing now. So any instruction now executed, it's loaded inside the instruction register. Input register and output register are a special type of registers that can read from the input device directly, or they can send the data or the result directly to the output device. Now, any question? Any question? Is it clear the registers؟ واضح الريجسترز؟ واضحة؟ هذا أهم شيء بالماري. فهمنا الريجسترز رح نفهم أي كود. ما فهمنا الريجسترز رح يكون الكود صعب عليكم. عندكم أي سؤال على الماري على الريجسترز؟ keeping silent يعني واضح. طيب. Now, buses will connect the registers as well. Mary cannot transfer the data into or out of the register without bus, data line bus, to transfer the data between the components. So in Mary, we assume that we have a common pathway. We have a multi-point bus. We have a multi-point bus. Okay? So the registers interconnected, they are also connected with the main memory through the common data bus. A unique number that is set on the control line whenever the data device is required to carry out the operation. What does that mean? All the registers connected together by using a common pathway. This is the common pathway, the L1. So if I want to send, for example, from the memory address register to the accumulator, for example, it will go through this. From 1, we will move to the accumulator or to the program counter, I said, sorry. So we must go through this common pathway. There is no direct connection. But we have a direct one between the MAR and the main memory address register. We have between the accumulator and the memory buffer register, between the memory buffer register and the ALU, between the ALU and the accumulator. Otherwise, we must use this common pathway. So from the MAR to the IR like this, from here to here. Now, what we said about the instruction register. In the instruction register, we said the size is 16 bits. The instruction register holds the instruction that is currently, immediately executed in the CPU. Now you need to understand something very important. The instruction register is 16 bits divided into 2 parts. Operation code, OBC, let me say code, and address. Operation code and address. Now, the address is 12 bits. and the operation code, it's what? 4 bits. So the address from bit 0 to bit 11, because we start from 0. From 12 to 15, it's the operation code. What does that mean? If you have this, for example, 1 0 0 0 0 0 0 0 okay, 1 0 1 1. So this part is the address in the main memory. This one, what we want to do, what the value will do, the operation. So 4 bits is the operation, 12 bits is the address. واضحة هذه? Because I'm about to explain a final exam question. In the final exam, they will give you 16 bits and they will ask you which instruction this one. Which instruction? So you will convert the 16 bits to instruction. So instruction or ISA is the interface between the computer hardware and software. Some ISA include hundreds of different instructions for processing and controlling the program execution. But for Mary, we will only study 14 or 13 instructions. Now, the instruction size in Mary 16 bits. From bit 0 to 11 is the address. From bit 12 to bit 15, what the ALU should do. So, if we have 4 bits for the operation, what's the maximum number of operations we can do? 2 to the power 4, 16. And you will not study all of them. So, now this is the main instruction we are going to use to write a Mary code. Okay? Now, as you see, load, store. Now, I will not, X is address. X is the memory address. Load the address X. Store X. Add the address X. Subtract X. Input, output without address. Halt without address. Skip condition. Also, it will be without address. Jump X. Go to address X. Now, load X. What's the binary representation? 1 0 0. So if we have inside the instruction set the ISA, in the operation code we have 1 0 0 0. What does that mean? It's load. Here we will get an address. Okay? For example, if in the operation code I have 2 0 1 0 0, so the instruction is stored. Yes, otherwise you will not answer it. Yes, ya Mu'taz, unfortunately yes. You need to memorize it. Only this part. Or this one, the hexadecimal representation. Number 3, add. So 1 1 0 0. 1 1 0 0, it's number 3 actually. 1 plus 2. 3. Instruction number 4, subtract X. Instruction number 5, input. This is the binary representation. Instruction number 6, output. 7, terminate, exit. This is the half, exit. Exit, stop the execution. Skip condition, it needs explanation, leave it. Jump X, put inside the program counter the value X. Okay, so it's number 9. So I will explain each one of these. Before I explain it, let us understand the ISA. Suppose I will skip this one because I'm sure 100% it will be very difficult now. Here, later it will be very simple. Now, for example, if we have this is the final exam question format. Suppose we have the following 16 bits instruction. What is this instruction? What's this instruction? Now, you already know that the instruction set divided into two parts. 12 bits for the address and 4 bits to the operation. Now, what we have in the operation code? 1000. So, based on this table, 1000, which operation? Load. So the operation is what? Load. Okay? Now, what we have in the 12 bits for the address? 111 zeros. Now 111, which number? Number 7. So load the address 7. This is the instruction we are going to execute. واضح? So the left 4 or most 4 bits, the operation code. Based on the table, this one is number 1. Number 1, the operation load, or the instruction load. Now the remaining 12 bits is number 7. So what the instruction will do? Will read the data find in address X, which is 7, copy its content to the accumulator. Now, one more example. 1100, the operation code. So based on the table, 1100 is what? Add. So we'll add the address X. Now X here, the address. The other 12 bits is what? Convert this one. Okay. So it will equal 14. So in hexadecimal, what? Add 00E. Number 14 is E. So we'll add the content located in address 14 to the accumulator with the value in the accumulator. So is it clear how we can read an instruction? Is it clear? Clear? It's difficult. Once you know the number of each operation, just you can know which instruction. The other 12 bits, it will be what? The address. Now, I need to explain this. It's very important. I need to explain this table. Now, load X, or for example, load 100. What this one will do? It will go to the memory. It will go to the memory at address 100. Suppose this one is the address 100. It will copy the data in address 100 to the accumulator. So if we want if we have number 10 inside address 100, the accumulator value will equal 10. So this is load X. Go to address X, copy the content located in address X inside the accumulator. Now store X. Store X. Store 150. Suppose inside the accumulator we have 30. Copy the content of the accumulator to the main memory, store them in address 150. So what we will have in address 150 after we store? 30. Okay? Add X now. Is the first two instruction clear? Load X, we will copy what we have in address X to the accumulator. Store X, we will store what we have in the accumulator in address X. واضح؟ Now add X. Add X. Suppose this is the memory address X. We have the value 10. And this is the accumulator, and we have in the accumulator 5. Now add X. What it will do? It will add, it's equal the following. The new accumulator value equal the old accumulator value plus the value in address X. So what add will do? Will add the data at address X with the old data in the accumulator and store the result in the accumulator. So it's like we are doing this. It's 5 plus 10. So what's the result? 15. Where we will store the 15 as a new result? In the accumulator. So add X, add the content of address X to the content in the accumulator and store the result in the accumulator. Subtract or sub-TX. Subtract the content of address X from the content of the accumulator and store the result in the accumulator. So AC equal the old value minus the data at address X. Input from the input device or from the keyboard to the accumulator. Output from the accumulator to the screen. Clear? Now halt, it's like Control D, Control X, exit, stop the execution. Now jump X, load the value of X into the program counter. Now jump, suppose we are executing the instruction number 6, so the program counter will be 7. Now we execute this one, jump 15. What we will do? The program counter value will become 50. واضح? I did not explain this. I still did not explain this. So, is it clear? Load X, quickly read the content of address X to the accumulator. Store X, load what we have in the accumulator to the memory at address X. Add X, add the old value of the accumulator with a value at address X and store the result in the accumulator. Subtract X, X always is address. Subtract the old accumulator value from the data at address X and store the result as well in the accumulator. Input from the keyboard to the accumulator. Output from the accumulator to the screen. Halt, stop, exit, terminate. Jump X, load X to the program counter. Now what about this skip condition? Okay, I'm going to explain it here. Now what's the number of the skip condition? It's 8. Okay, if we have a skip condition, okay, if the operation is a skip condition. Now what we said about the ISA is 16-bit from 0 to 11, from 12 to 15. If the operation code is a skip condition, now we will use these two bits, the bit number 10 and the bit number 11. We need them. Why we need them? Now, one important instruction is a skip condition or skip cond here. Skip condition, when the skip condition is executed, the value stored in the accumulator will be checked. If we have a skip condition here, okay, we will check the accumulator value. So what we have here will be checked. Is it less than 0, greater than 0, or equal 0? Okay? So, if the condition is true, now if the condition is true, the next instruction will be skipped. If the condition is false, the next instruction will not be skipped. This is how the skip condition is worked. Skip condition is logical condition, logical question. If it's true, the next instruction will be skipped. So if it's true, I will say what? BC equal BC plus 1. The program counter equal program counter plus 1. If the condition is false, I will not increment the program counter by 1. Now, how will it check if the value inside the accumulator less than 0, greater than 0, or equal 0? By check the bit number 0 and the bit number 11 in the address. If bit number 10 and 11 equal 0, 0, so what's the condition? We are checking if the accumulator less than 0. If here we have 0, 0. If we have 1, 0, we are checking if the accumulator equals 0. If we have 0, 1, so 0, 1, 2 actually, we are checking if the accumulator greater than 0. So, skip condition, it's a condition. We will check the accumulator. So the result either true or false. If it's true, we will increment the program counter by 1. If it's false, we will not increment the program counter by 1. Now how we will know we are checking if the accumulator less than 0, greater than 0, equal 0 by testing the bit number 10 and 11 in the address. If it's 0, 0, which means if the accumulator less than 0. If it's 1, 0, is the accumulator equal 0. If it's 0, 1, if the accumulator greater than 0. So as you see, always the address will be 0, 0. Always. So 1, 2, 4, 8. So the operation code is 8. The operation code is 8. So it's a skip condition. Now what's this number in hexadecimal actually? It's 400. In hexadecimal it's 400. So it's 1, 0. 1, 0. So skip condition what? 400. The accumulator equals 0. 400 is the hexadecimal representation. 12 bits hexadecimal representation. Okay? If it's 0, 0, which means we are checking if the accumulator less than 0. We'll write it like this. Skip condition 0, 0, 0. 3 bits representation. If it's 1, 0, which means the accumulator greater than 0, we'll write skip condition 800. Clear this one? So, how will we skip the next instruction? By add 1 to the accumulator. AC equal EC plus 1. DC, sorry. The program counter. Now, 400 800 are in base 16 representation. So they are equivalent to what? To 12 bits address representation. Clear? So in the program, you can write skip condition 000, which means you are testing if the accumulator less than 0. Skip condition 400, the accumulator equals 0. Skip condition 800, the accumulator greater than 0. Any question? Any question? Now, we discussed already the registers type, the task of each register. We explore the 9 instructions and we understand what each one will do when we use it in our code. Now, my question is the following. When I said load X, what load X will do? It will go to the address X, it will copy the content of address X, add them to the accumulator. Okay, clear, simple, easy. I agree with you. I have a question here. Based on this, do I have a direct connection between the accumulator and the main memory? No. So how the data will be loaded in the accumulator? Store X. Store X. Store the data in the accumulator in the main memory at address X. So is there any connection between the main memory and the accumulator to copy the data from here to the main memory at this address? No. So what does that mean? There is a sub-steps will be executed when we go through each operation or each instruction. So it's not direct. Only 2 instructions are direct, input and output. Only direct. Otherwise, we need to understand exactly what will happen when we execute. So how we can understand exactly what are the sub-operations, what are the micro-operations that are executed when we execute each instruction. To understand exactly what are the sub-operations, we need to represent what will happen. So how we will represent what will happen? By using the RTL or the RTN, the register transfer language or the register transfer notation, and in the final exam they will ask you to write the RTL for a specific instruction. If you really understand what each register do, you can write it immediately without memorizing. So what's the RTL or RTN? They show you exactly what will happen when I said load X, add X, store X, skip condition, jump X. So we'll see exactly what happened in each register when we execute that instruction by using the RTL, or it's called same RTN, register transfer notation. Before we start, we need to agree about the following. When I say MX, which means what? The actual data, okay, value is stored in memory address X. Okay? This notation, يعني هذا التعبير، أنا بتكلم عن الداتا اللي موجودة بالميموري بأدرس X. The arrows and the column transfer a byte from the memory to the register or from the register to the memory. Okay? So actual data, transfer data. Now check. Load X. What load X will do? It will go to the computer main memory. This is the computer main memory. We have X and data, it will load the data in the accumulator. Remember, only the memory address register connect to the main memory. Only the memory buffer register will read the data. So, what will happen when I say load X? The address X will be placed in the memory address register. The data that are located in that address, which now loaded in the MAR, will be copied to the memory buffer register. Now I know that there is a direct connection between the accumulator and the memory buffer register. So from the accumulator to the, from the memory buffer register to the accumulator. صعب هذا؟ So we copy the address to the memory address register. We go to that address, copy the actual data to the memory buffer register. Then from the memory buffer register to the accumulator. Store X. We need to store the data of the accumulator at address X. So we will place the address X inside the memory address register. We will place the data to the memory buffer register. Now the data from the memory buffer register will be placed in the main memory at this address. Remember, we copy the address to the memory address register. Is it clear? واضح هذا؟ واضح؟ إذا فاهم بالضبط كل ريجستر إيش بيعمل بتكتبه بدون ما تتذكره. بشرط تكون فاهم كل ريجستر إيش بيعمل. الآن add X. We will add the content of address X to what? To the accumulator. So same. We will load the address X to the memory address register. We will copy the data to the memory buffer register. Now the new accumulator equal the old one plus the memory buffer register data. Subtract. Just instead of add, subtract. What we call this? RTL, RTM, register transfer language or register transfer notation. Now, input from the input register to the accumulator. Output from the accumulator to the input register. Halt doesn't have any RTL. Halt means exit, terminate. Now jump X, the address X will be loaded to the program counter. Now skip condition, now we are checking the bit number 10 and the bit number 11. If they equal 0, 0, which means the accumulator less than 0, so we'll increment the program counter by 1. If it's 1, 0, which means the accumulator equals 0, so BC, the new BC equal the old 1 plus 1. If it's 0, 1, the accumulator greater than 0. If it's true, we will increment the program counter by 1. Now, finally, if we have a look to the machine cycle, or the clock cycle of the CPU, it's worth to mention that the Mary, like any other computer architecture, follow the basic CPU cycle, fetch, decode, execute. So the fetch, decode, execute cycle is a series of steps that the computer carries out when it runs the program. So we first fetch the instruction from the memory, place it to the instruction register. Once we place it inside the instruction register, we will increment the program counter by 1. Why? To know the next instruction to be executed. So this is the fetch. Copy the BC to the memory address register, which means go to that address, copy the instruction to the instruction register, then increment the program counter by 1. So we're done with fetch. Once the instruction register is decoded, now we first fetch the instruction to the IR. Once the IR is decoded, we determine what we need to do next. Why? So BC equal BC plus 1. Now decode the instruction in the instruction registers. We'll check the address of bits 0 and 11 to the address, from 12 to 15 to the instruction register. So we are decoding. Now, do we need any other data? If yes, we will copy them by using the MAR and MBR. If no, we'll execute the instruction. Then we will move back to new fetch decode execute cycle. So, this is what will happen at each fetch decode execute, but what we add the registers that we will use. We use the program counter at the beginning. We'll copy the instruction to the instruction register, so we're done with the fetch. We'll increment the program counter by 1. Then we'll check the operation inside the IR. We'll check the bits from 0 to 11. Then we'll ask, now this one, it means a question. It has either yes or no answer. Do we need any other operands, any other data? If yes, we'll use the memory address register and the memory buffer register to read or load that data. If no, we'll execute the instruction, we'll replace the result in the accumulator, and we'll go through a next cycle. Now, I would like to ask you, do you want me to carry on? Or, okay, next week we will cover the TMA. Now, next week I will explain a simple code. Once I explain this is the register transfer notation. So it will be very simple to you. So next class, I can cover the full chapter and I can discuss with you the TMA on 24. Is it okay? So we'll have 4 days to do the TMA. Actually, the TMA can be done within 15 minutes. The online assignment can be solved within 10 minutes actually, not 15 minutes, 10 minutes. So is it okay? Fine, okay, I will stop here. So next class, I will explain to you how to write a simple program, how to run a simple program, and I will discuss with you the TMA. It's very simple, trust me. You can do it within 10 minutes. Not more than that. Any question? أي سؤال؟ Okay, so you can review for the exam. Inshallah, yani, good luck tomorrow. And don't worry, practice, you will solve any question simply and easy. Yalla, good luck and see you next week, inshallah, on the same class time. Just print the screen so you can leave now. يعطيكم العافية.